forever. The idealization is correct, and that if there were no influences acting, such as the friction on the floor and so on, the thing would go at a uniform speed forever. The next point was made by Newton, who discussed the next question, which is when it doesn't go in a straight line, then what? And he answered this way, that a force is needed to change the velocity in any manner. First, for instance, if you're pushing it in a direction that it moves, it will speed up. If you find that it changes direction, then the force must have been sideways. And that the force can be measured by the product of two effects. First, how much does the velocity change in a small interval of time? How fast is the velocity changing? How much is it accelerating in this direction, or how much is the velocity changing when it changes direction? That's called the acceleration. And when that's multiplied by a coefficient called the mass of an object, or its inertia coefficient, then that together is a force. One can measure for instance, if one has a stone on the end of a string and swings it in a circle over his head, then one can measure, when one finds one has to pull, the reason is that the speed of the velocity, the speed is not changing as it goes around the circle, but it's changing its direction, so there must be perpetually an in-pulling force, and this is proportional to the mass, so that if we were to take two different objects, first swing one, and then swing another one at the same speed around the head and measure the force in the second one, that second one, the new force is bigger than the other force in the proportion that the masses are different. This is a way of measuring the masses, by how hard it is to change the speed. Now, then Newton saw from this that, for instance, to take a simple example, if a planet is going in a circle around the sun, no force is needed to make it go sideways tangentially. If there were no force at all on it, it would have just keep coasting this way. But actually, the planet doesn't keep coasting this way, but finds itself later not out here where it would go if there were no force at all, but further down toward the sun. In other words, its velocity, its motion, has been deflected toward the sun. So what the angels have to do is to beat their wings in toward the sun all the time, that the motion to keep it going in a straight line has no known reason. The reason why things coast forever has never been found out. The law of inertia is no known origin. So the angels don't exist, but the continuation of the motion does. But in order to obtain the falling operation, we do need a force. So it became apparent that the origin of that the force was toward the sun. As a matter of fact, Newton was able to demonstrate that the statement that equal areas are swept in equal times was a direct consequence of the simple idea that all of the changes in velocity are directed exactly to the sun, even in the elliptical case. And maybe I'll have time next time to show you how that works in detail. So from this law, he would confirm the idea that the force is toward the sun. And from knowing how the periods of the different planets vary with the distance away from the sun, it's possible to determine how that force must weaken at different distances, and he was able to determine that the force must vary inversely as the square of the distance. Now, so far, he hasn't said anything. Yes, because he only said two things which Kepler said in a different language. One is exactly equivalent to the statement that the force is toward the sun, and the other is exactly equivalent to the statement that the law is inversely as the square of the distance. But people had seen in telescopes the Jupiter's satellites going around Jupiter, and it looked like a little solar system, so the satellites were attracted to Jupiter. And the moon is attracted to the Earth, and this goes around the Earth, is attracted the same way. So it looks like everything's attracted to everything else. And so the next statement was to generalize this and to say that every object attracts every other object. If so, the Earth must be pulling on the moon, just as the sun pulls on the planet. But it's known that the Earth pulls on things because you're all sitting tightly in your seats in spite of your desires to float out of the hall at this time. The pull for objects on the Earth was well known in the phenomenon of gravitation. And it was Newton's idea then that maybe the gravitation which held the moon in the orbit also applied was the same gravitation that pulled the objects toward the Earth. Now it is easy to figure out how far the moon falls in 1 second. Because if it went in a straight line, you know the size of the orbit, you know it takes a month to go around, and if you figure out how far it goes in 1 second, you can figure out how far the circle of the moon's orbit has fallen below the straight line that it would have been in if it didn't go the way it does go. And this distance is 1/20th of an inch. Now the moon is 60 times as far away from the Earth's center than we are. We're 4,000 miles away from the center, and the moon is 240,000 miles away from the center. So if the law of inverse square is right, an object at the Earth's surface should fall in 1 second by 1/20th of an inch times 3,600, being the square of 60, because the force has been weakened by 60 times 60 for the inverse square law in getting out there to the moon. And if you multiply a 20th of an inch by 3,600, you get about 16 feet. And lo, it is known already from Galileo's measurements that things fell in 1 second on the Earth's surface by 16 feet. So this meant, you see, that he was on the right track. There was no going back now. Because a new fact that was completely independent previously, which is the period of the moon's orbit and its distance from the Earth, was connected to another fact, which is how long it takes something to fall in 1 second. So this was a dramatic test that everything's all right. Further, he had a lot of other predictions. He was able to calculate what the shape of the orbit should be if the law were the inverse square, and found indeed that it was an ellipse. So he got 3 for 2, as it were. In addition, a number of new phenomena had their obvious explanations. One was the tides. The tides were due to the pull of the moon on the Earth. This had sometimes been thought of before, with the difficulty that if there's the pull of the moon on the Earth being here, the water's being pulled up to the moon, then there would only be one tide a day where that bump of water is under the moon. But actually, you know, there are tides every 12 hours roughly, and that's 2 tides a day. But there was also another school of thought that had a different conclusion. Their theory was that it was the Earth that was pulled by the moon away from the water. So actually Newton was the first one to realize what actually was going on, that the force of the moon on the Earth and on the water is the same at the same distance, and that the water here is closer to the moon and the water here is further from the moon than the Earth, than the rigid Earth, so that the water is pulled more toward the moon here, and here is less toward the moon than the Earth, so that it's a combination of those 2 pictures that makes a double tide. Actually, the Earth does the same trick as the moon. It goes around a circle, really. I mean, the force of the moon on the Earth is balanced, but by what? By the fact that just like the moon goes in a circle to balance the Earth's force, the Earth is also going in a circle. Actually, the center of the circle is somewhere inside the Earth. It's also going in a circle to balance the moon. So the 2 of them go around a common center here, and if you wish, this water is thrown off by centrifugal force more than the Earth is, and this water is attracted more than the average of the Earth. At any rate, the tides were then explained, and the fact that there were 2 a day. A lot of other things became quite clear. Why the Earth is round, because everything gets pulled in. And why it isn't round, because it's spinning so that the outside gets thrown out a little bit and it balances. And why the sun and moon are round, and so on. Now, as the science developed, and measurements were made ever more accurately, the tests of Newton's law became much more stringent. And the first careful tests involved the moons of Jupiter. By careful observations of the way they went around over a long period of time, one could be very careful to check that every